Righty, hey folks, how we doing? Good to see you guys. So let's see here. Let's go and share a little bit with y'all. There we are. All right, so we're getting ready to start our final unit of 2020, and that deals with getting ourselves ready to make that jump into calculus and dealing with something called a limit. Now, a limit it's not exactly what we've been doing before. Where we actually say f of x or f of 3 equals some number. That's a function value. Function values equal something. Limits, it's the idea that we get really, really, really close to something, but we don't necessarily quite get there. Like, for instance, I'm going to get really, really, really close to this value, but I don't quite get there. You get really, really, really close to this value, but I don't quite get there. It's that idea of where does the graph look like it's going, and not necessarily what the exact actual value is, because the value is just a sliver in time. It has no length or width or anything. It's just an exact value, where a limit says it's getting really close to something. What's it getting to? And so say that we call this right here, say we call that C, and we call this the value L. So we'd say the limit as x approaches C. In other words, when x equals C, not quite equals C, but gets really, really close to it. When x is approaching C, that arrow means approach. F of x looks like it is going to this y value, this L value. Realize that's not what the f of x actually has to be. It's just, what does the graph look like it's going to, not exactly what it is. It's what is the graph going to from the left and right side as it gets really close to? What's it going into? What's it coming out of? What's that value? So limits can exist at holes where function values can't. And so there's a quick little difference we usually make. First of all, with limit values, we say limits can exist or limits don't exist. And for those that have seen the movie Mean Girls, we would channel our inner mean girl and say the limit doesn't exist. And we'll do that quite a bit during the course of this chapter here. And then we also have function values. Function values, they are either defined or undefined. So that's something that we need to remember as we go through this whole idea here. We're going to be dealing with two different things, function values and limits. Primarily, we're going to be dealing with limits. So like limit would be not what the value is, it's what does it approach. So the limit can either exist and be equal to some value L, or the limit doesn't exist, which we'll get to. And then the function value, well, that's the exact value that you plug in. So when you plug it in, what do you get? So notice the function value from our picture, our function value doesn't have to equal the limit value. So as we keep going on here, we're going to be dealing with what a limit actually can go to. And now a limit exists when it goes to an exact value. Now it can be either a whole or it can be a function value. For instance, right here, notice for this function s of x, as x approaches 2. So if I take my graph here and I come up from 2, as x approaches 2, what value am I going into from the left and the right? And again, this one's a whole. Now it's okay that it's a whole because that whole is so tiny and minuscule. We're not actually finding exactly when x is 2. We're finding just what it gets close to. So we'd say then that the limit equals 2. I'm sorry, that the limit equals 4. As x approaches 2, the graph goes to 4. It doesn't matter if it's an open dot or a closed dot. It's just what is it going to. Over here, when x approaches 2, notice on this one, we actually have a closed dot, and that works too. It doesn't matter if it's an open dot or a closed dot for them. It's just the graph goes in and out of the same value. If that happens, we say that the limit graphically exists. We can evaluate the limit from a graph by what does it go in and out of. So that's what it looks like when a limit exists. What about when a limit doesn't exist? Well, there's three types of those when a limit doesn't exist. The first one, and this is where we would get to the mean girls thing, the graph goes to infinity, or can go to either negative infinity, or it could go to positive infinity. So as that graph comes up here, if it looks like it's going to negative infinity or positive infinity, we say that the limit doesn't exist. We say it doesn't exist because it's unbounded. So the limit, look, on one part it looks like it's going to negative infinity, the other part it's going to a positive infinity. At this point, we would say the limit doesn't exist because the limit is this idea of we're trapping something into a set value. Well, if we're going to infinity, we're going out forever to infinity and beyond. We can't go there. Only Buzz Lightyear can. We have to go to a set value. So we'd say that in this case, the limit doesn't exist. Now, over here, notice what happens. At x equals 1, from this left side, the graph goes to one value, while to the other side, the right side, the graph is going to a different value. It doesn't go to the same value. So again, we'd say the limit does not exist. So actually, I should have wrote that over here too. Sorry about that. Let me do that real quick. Once you say it goes to infinity, you should actually finish off and say, well, that means the limit doesn't exist. Does not exist. So on this other one here, that notice it doesn't go to exist because it doesn't exist because it goes to two separate values. So since the graph two different y values at x equals 1, the limit does not exist at x equals 1. Again, we're trying to trap it in between these two functions. Well, if they don't go to the same thing, then that means our limit doesn't go to a single specific place. Now we have a special name for this type of one. We call this type of break, and we'll talk more about it. Eventually we'll call it a point of discontinuity. We call this a jump discontinuity. Because it looks like the graph is going to this b value, then all of a sudden it jumps up to where c is, and then it keeps going for this piecewise function. That's called jump discontinuity. All right, this other thing here is as you get really close to a value, the graph just starts going crazy. Notice it's coming down, it's going up, it's coming down, and then it gets really super close, and then eventually kind of goes back out again. So as we approach 0, it keeps bouncing back and forth. And because of that, we say that in this case, the limit also does not exist. So there's three different types that doesn't exist. Doesn't exist at a vertical asymptote. Doesn't exist at a jump discontinuity. And then this other place where the graph does not exist, we call this is where the graph oscillates. Since f of x oscillates, at x as x approaches 0, then the limit of f of x does not exist at x equals 0. Since it starts to oscillate, it starts to bounce up and down, the limit then does not exist at that value. So 3 different times the limit doesn't exist. When it goes to a vertical asymptote because it's unbounded, when it approaches 2 different y values because the function jumps, and when it just starts oscillating back and forth because we don't know exactly where we are. So limits can exist at a hole or a closed dot if it goes in and out of the same value. But there's 3 times where it doesn't exist. So let's see if we can play this a little bit from a graphical standpoint. Remember, function values are defined and undefined, while limit values exist or don't exist. So let's see if we can't figure this out. When x equals -3, how about I do all the function values first? All right, so when x equals -3, so I'm going to draw this line straight over here. What is the value that I'm going to? Looks like I'm going to the value 0.7. So I would say then that this is equal to a 0.7. What about f of -2? Well, that's right here. That's 0. At -1, notice what happens here. We have this this line going up. So that means it is undefined because we have a vertical asymptote. So when we're doing function values, all we're looking for are solid dots. When it's 1, where's 1 at? Right about here. So what is that value? Looks like it is the value about -1.9. So we'll throw that on here. And 2, remember, it's always a solid dot. It's not where the graph goes, it's where the solid dot is. So here's my solid dot, and the solid dot is at -1. Why don't you guys go ahead and pause the video and see if you can actually do the limit values. Go for it. All right, let's see what happens here. So I go into 1, but notice on the other side, I approach a different value. I don't go to the same value, so that means the limit does not exist. The reason why it doesn't exist, this is a jump discontinuity. It doesn't exist. At -2, I'm going into -2. From the left, I'm going into 0 from the left and going into right 0 from the right. So therefore, since it goes to the same value, that means it equals 0. Notice again on that first one, we had a function value. It was defined, but the limit didn't exist. On the second one, I'm going to infinity, and I'm going to infinity. So I'm not going to say that it goes to positive infinity. I mean, I could say it equals positive infinity. So if I want to say that's fine, but I need to do a little bit more with it than that. If it goes to positive infinity, it is unbounded. So the graph, the limit at x equals -1 does not exist. Here at 1, I'm going down to this value, and I'm going down to the same value. I'm going to the same value, so that equals whatever that value is. It's -1.9. And on this one, notice I'm going into the hole from the same side, left and right. Even though I have a solid dot, I'm not going to the solid dot. I'm going to the. That's not what I wanted. Do that. That's kind of funky looking. I'm going in and out of the same dot. Therefore, it is going to be that value right there. So it's -0.5. And again, take a look at this last one. The function value and the limit, they go to different values. That's okay. Function values are closed dots. Limit values are when the graph goes in and out of the same value. So last thing we're going to talk about is that's how we evaluate them by graphing. How do we evaluate them analytically? Or in other words, how do we essentially plug them in? So to evaluate analytically, basically whatever this value is here, whatever x approaches, just plug it into your function. So the biggest thing here, don't overthink it, just plug it in. So 2 cubed minus 3 times 2 squared minus 7 times 2 plus 8. See, they ask you to evaluate it analytically, all you're doing is just plugging it in. So go ahead and pause the video and evaluate these next two analytically. All right, friends, let's see how you guys did here. We have the square root of 2 times 4 plus 17. So that's the square root of 25, which is 5. And this is majority of what limits is. You just plug it in. We don't want to overthink it. We just plug it in. So 3 times negative 5 minus 1 all over 2 times negative 5 plus 7. So negative 16 all over, oh, what's that going to be? Negative 10 plus 7 is negative 3. And negative 16 over negative 3, that would be a positive 16 thirds. All right, well, let's try just a couple more here. Go back to the past a little bit here, a little bit of trig. Why don't you, and this is about the extent of the trig you do in calculus, is can you evaluate trig values? Can you evaluate arc trig values? So why don't you guys go ahead and pause the video and try these real quick. All right, let's see how you did. So we have sine of 2 pi over 3 plus tangent of 2 times 2 pi over 3. So sine of 2 pi over 3 plus tangent of 4 pi over 3 Oopsies, there we are. And we end up with sine of 2 pi over 3 is a positive root 3 over 2. And tangent of 4 pi over 3 is a positive root 3. So if I put this over 1 and I multiply top and bottom by 2, I get root 3 over 2 plus 2 root 3 over 2, which would be equal to 3 root 3 over 2. And the last, and certainly at least, we plug in our last one here. We have arc cotangent of negative 4 over 4, which is the same thing as arc cotangent of negative 1. So we're trying to figure out when does our graph, our arc cotangent, equal negative 1. So we go back to an oldie but a goodie here. We get rid of our no-fly zone. Can't be on the left-hand side here. And for our graph, negative 1 would be down here. And that would be the value negative pi over 4. So arc cotangent of negative 1 is equal to negative pi over 4. So we just, again, when we're evaluating analytically, you just plug numbers in and figure out what you get. All right, friends, that ends our first kind of day here. So good luck, and I'll see you guys in the morning. All right, take care.